in the topic interaction of radiation with matter. In this class, we will discuss interaction of gamma rays. The interaction mechanisms for gamma rays in matter are 1. Photoelectric absorption, 2. Compton scattering, 3. Pair production, 4. Coherent scattering, and the fifth one, photonuclear disintegration. From these, only the first three play an important role in radiation measurements. All these processes lead to the partial or complete transfer of the gamma ray photon energy to electron energy. They result in sudden and abrupt changes in the gamma ray photon. The photon either disappears entirely or is scattered through a significant angle. This behavior is a marked contrast to the charged particles and electrons. It means this one, it suddenly disappears and scattered through a significant angle. And this is not this type behavior we have not seen in fast moving electrons as well as heavy charged particles. At low energies, the photoelectric interaction dominates. Compton scattering is present at all energies and pair production dominates at very high energies. So these are the three important ones. So we will start with the photoelectric absorption. In the photoelectric absorption process, a photon undergoes an interaction with an absorber atom in which the photon completely disappears. In its place, an energetic photoelectron is ejected by the atom from one of its bound shells. The interaction is with the atom as a whole and cannot take place with the free electrons. For gamma rays of sufficient energy, the most probable origin of the photoelectron is the most tightly bound or K shell of the atom. That means the innermost shell of the atoms. So from there, the first possibility is from there. And the photoelectron appears with an energy given by E energy of electron equal to h nu minus Eb, where Eb represents the binding energy of the photoelectron in its original shell. And for gamma rays for more than a few hundred kilo electron volts of energy, the photoelectron carries off the majority of the original photon energy. That means if this value is very large, a few hundred kilo electron volt we have mentioned here, and as you know, the binding energies are of the order of electron volts. So most of the energy is carried away by the electrons as its kinetic energy. And after the photoelectric effect, the atom is said to be ionized and there is a vacancy in the orbit. And this vacancy is quickly filled through capture of free electron. There we are using the term and or rearrangement of electrons from other shells of the atom. So if there is a vacancy in K shell, it can be replaced with another electron from the higher orbits. The difference in orbital energy is released as characteristic X-ray or Auger electrons, and this is known to us. The difference in energy is normally emitted as characteristic X-rays that we have discussed in the X-ray mechanism that we have already done. And the photoelectric process is the predominant mode of interaction for gamma rays of relatively low energy, and this is also true for X-rays. And the process is also enhanced for absorber materials of high atomic number Z. No single analytic expression is valid for the probability of the photoelectric absorption per atom. That means in from a particular atom, how many photoelectric absorption is possible? That is not given by any analytical expression, and that you are calling it as a photoelectric coefficient tau over all ranges of E gamma and Z. But a rough approximation is your tau, that means photoelectric coefficient, which is the probability of occurring that photoelectric absorption. It will be nearly a constant into Z raised to n by E raised to gamma raised to 3.5. In some books, you are getting seeing this as Z cube by E cube, where the exponent n varies between 4 and 5. Value of n is 4 and 5 over the gamma ray energy region of interest. It means the normal region that we are taking. This severe dependence of the photoelectric absorption probability on the atomic number, that means this value is nearly 4 or 5. So it is a severe or a huge quantity. That is why you are calling, mentioning by this term, severe dependence is a primary reason for choosing of high Z materials such as lead in gamma ray shields. So as gamma ray shields, you are normally using lead. Lead has a high atomic number. So you will be always using high atomic number materials as gamma ray absorbers. And if you are using, this is the term something more commonly used, that tau by rho is called for, that means this is for our density, and this is called mass photoelectric attenuation coefficient, and this you are normally calling as the photoelectric coefficient tau dividing by density, you are calling it as mass photoelectric attenuation coefficient. And this graph shows the variation of that tau by rho with the photon energy for both lead and for aluminium. You can see that this Z is having a high atomic number of 82 and aluminium a small atomic number of 30, and it is shown in figure. You can see that this photon energy and increase in photon energy, and this is tau by rho is also increasing here, and for aluminium it is almost a straight line, and here you can see some peaks. You have marked them as L edge, K edge, etc., and we will explain them. So here also in general you can say that as the photon energy increases, tau by rho decreases. And we have mentioned that this is dominant normally at low energies. From the diagram, a number of important features can be seen. This is over a wide range of photoelectric absorption probability for lead. Is some 250 times as great as the value for aluminium. Actually, this what we have mentioned is over a wide range, the photoelectric absorption probability of lead is nearly 250 times as that of aluminium, because the ratio of their atomic mass is cube of their atomic mass is nearly 251 is to 1. Actually, we have used it as a cube here. As I have already mentioned, in some books you are getting the ratio as Z cube. So that ratio is somewhat higher. And for both materials, the absorption coefficient decrease as the energy is increased. This we can show from the graph, or we can see from the graph. And there are sudden breaks that occur and produce sudden departures of the smooth variation. That we have seen here, a sudden departure, or otherwise it is a smooth variation. These sudden changes in the attenuation of the radiation occur at photon energies equal to the binding energies of different electronic shells. If the gamma ray photon energy is equal to the K shell binding energy, the absorption increases steeply. This sharp discontinuity in the plot is called the K edge absorption, and similar absorption edges occur at lower energies for LM electron shells. That means this is the K edge absorption. We have mentioned that as energy increases, the tau by rho is decreasing. But when that energy is equal to the binding energy of electron in the K shell, they are trying to emit. So there you can see a sudden absorption. That means a sudden increase in the absorption coefficient. And as we know, this K has the binding energy of K is larger than L. So here you can see L. And for some materials you can even see the higher orders M and etc. And we have the next interaction phenomena known as Compton scattering. The interaction process of Compton scattering takes place between the incident gamma ray photon and an electron in the absorbing materials. It is most often the predominant interaction mechanism for gamma ray energies typical of radioisotope sources. And in Compton scattering, the incoming gamma ray photon is deflected through an angle theta with respect to the original direction. The photon transfers a portion of its energy to the electron, and we are assuming that assumed to be initially at rest, that electron, which is then known as a recoil electron. And this is the figure. An incident photon is incidenting here, a photon is incidenting here. So that energy is given to one of the electron. So that electron is moving to this side, and this is the recoil electron. It is recoiling, and this is actually scattered through an angle, and that angle you are marking as theta, and the recoil electron angle you are marking as phi. Since all angles of scattering are possible, that means this can be either 0 or even 180 or maximum 90. That we will mention 90 and 0. The energy of the incident photon is equal to the sum of the energy of the scattered photon and the kinetic energy of the ejected electron. That means this incident energy equal to kinetic energy of recoil electron plus energy of the scattered photon. And you can see that the energy of the scattered photon will be less than the incident photon energy because a portion has been utilized for the recoiling of electron. And the expression that relates the energy transfer and the scattering angle for any given interaction can simply be derived by writing simultaneous equations for the conservation of energy and momentum. And in that equation you can write the expression for energy as well as momentum, and from that you will be getting h nu dash, that means the recoil energy, as h nu by 1 plus h nu by m0 c square into 1 minus cos theta. And you can see that this h nu dash will be equal to h nu only when this term you are getting as 0. That means your cos theta equal to 1. That means theta equal to 0. That means your electron is directly passing, where m0 c square is the rest mass energy of the electron. So you just look this equation, and based on this, if the photon makes a direct hit on the electron will travel straight forward. This one, a direct hit, your electron will travel directly. That means this phi will be equal to 0. And always actually, sometimes you can say that there is a relation between this angle will be equal to 90 degree. That is sometimes you are mentioning. And the gamma ray photon will be scattered back with theta equal to 180 degree. In that case, it is hitting here and this is moving directly. So this will be hitting back. And at that condition, what can you say? This theta is equal to 180 and this phi is equal to 0. And if theta is equal to 180, this will be minus 1. So this has least value. 1 minus 2 times this value. In this collision, the electron will get its maximum energy while the scattered photon goes with the minimum energy. That means from this expression you can see that this value is a minus 1 and you are subtracting a term from 1. So you can see that h nu will be minimum in that case. And if the gamma ray photon makes a grazing hit with the electron will be emitted at the right angles. That means phi is equal to 90 degree and the scattered photon will go in the forward direction. Like here. A grazing angle means this will go directly and the electron will be moving like this. That means phi is equal to 90 degree and this will be 0. In this collision, the electron receives minimal energy and the scattered photon goes with the maximum energy. That means here theta is equal to 0. So this is 0. So this is electron will get minimum energy and this will go with the maximum energy. The probability of Compton scattering, and I think we have mentioned a 90 degree here. It is normally saying that the maximum energy transfer you are observing, this is the general way we have mentioned it as 90 degree and I am not explaining such things here. The probability of Compton scattering per atom of the absorber depends on the number of electrons available as scattered targets and therefore increases linearly with the set. So the probability of Compton scattering increases with the increase in set because when Z increases, you have probability of hitting with the more electrons. And next is pair production. If the gamma ray energy exceeds twice the rest mass energy of an electron, rest mass energy of electron is 0.511 MeV, that you are getting as MEC square. So this 2 into 0.51 is 1.02 MeV, actually 1.022. We are taking it as 1.02 MeV. The process of pair production is energetically possible. So a photon having an energy greater than 1.02 MeV passing near the nucleus of an atom is subjected to a strong Coulomb field of the nucleus. And the photon may suddenly disappear. And we have mentioning that this photon actually it is the exchange particle in electromagnetic field. So your Coulomb force is a type of electromagnetic field. So the photon may suddenly disappear and create a positron and electron pair, and this is called pair production. So it is creating a pair of the electron-positron, that means matter-antimatter pair. And for each particle, 0.511 MeV is required, and the excess energy greater than 1.02 MeV would be shared between positron and electron as kinetic energy. And this process is an example for the conservation of energy or conversion of energy into mass as predicted by Einstein. So, we are saying that the rest mass energy of electron is 0.511 MeV, means when the mass equivalent to electron, or when an electron is completely converted as energy, that will be equal to 0.511 MeV. So, if you have double that energy will be converted as mass, which is the electron and positron pair. And this is a pictorial representation. This is the nucleus. When your incident photon is coming near, suddenly these two particles are appearing here, and this photon is disappeared. So, electron and positron. This is electron and this is positron, and this is the, you are mentioning here as the positive negative electron pair. The electron loses energy in the medium by further excitation, ionization, and filling in the vacancy in the orbital shells. So, that electron can again make collision, etc., etc., or they can excite. And the positron travels in the medium and loses its energy, similarly by ionization, excitation, and Bremsstrahlung process. Finally, the positron combines with the free electron. That means when the energy of that positron becomes very small, it combines with the free electron and annihilates. So, when matter and antimatter are coming together, you have the phenomena, or you have the process of annihilation. That means electron plus positron will give you 2 gamma, and that gamma are normally emitted in opposite directions, and these things we have already discussed. And this produces 2 photons of energy 0.511 MeV, which are ejected in opposite directions. The above process is called positron annihilation, and this is an example of conservation of mass, conversion of mass into energy. And this is the basis for positron emission tomography. I think you might have heard about PET or PET, positron emission tomography, which is something more advanced than your you are using normally this MRI, magnetic resonance imaging, and this positron emission tomography is more advanced that, or it is giving you more clear images than your MRI. So nowadays this is preferred, which is, and here this is the basis for your positron emission tomography, which this positron annihilation, that means electron positron annihilation, is the general principle that you are using here. And no simple expression exists for the probability of pair production per nucleus, but its magnitude varies approximately as the square of the absorber atomic number. So here also you can see that when mass number increases, or when the atomic number increases, you can get the possibility of pair production is increasing. And next is coherent scattering. In addition to Compton scattering, as you know, this Compton scattering is an example of inelastic scattering. So this is a type of coherent scattering, means an elastic type of scattering. In addition to Compton scattering, another type of scattering can occur in which the gamma ray photon interacts coherently with all the electrons of the absorber atom. This coherent scattering or Rayleigh scattering process neither excites nor ionizes the atom, and the gamma ray photon retains its original energy after the scattering event. So it just scatters. Coherent scattering is also known as unmodified or elastic scattering. This usually occurs when the energy of the gamma photon is much smaller than the ionization energy of the atom. And since no energy is transferred, this process is often neglected in basic discussions of gamma ray interactions. And when the direction of photon is changed in coherent scattering, all other interaction mechanisms of gamma ray must be taken into account. The probability of coherent scattering is significant only for low photon energies, typically below a few hundred kiloelectron volt for common materials, and it is most prominent in high Z absorbers. The average deflection angle decreases with increasing energy and further restricting the practical importance of coherent scattering to low energies. And this is the relative importance of the three major types of gamma ray interactions. The lines show the values of Z and H nu for which the two neighboring effects are just equal. So here along this line your photoelectric effect and Compton scattering have equal probability, and along this Compton scattering as well as pair production is dominant. And we have mentioned that in all energy rays, your Compton scattering is positive. But here, this photoelectric effect or photoelectric absorption is dominant only at lower energies and pair production at higher energies. And you can see that it is energy, this is MeV. So it is when greater than 1.02 MeV, then only this pair production is possible. The line at the left represents the energy at which photoelectric absorption and Compton scattering are equally possible as a function of the absorber atomic thickness. Atomic number Z of the absorber. So this term absorber atomic thickness, absorber atomic number. Compton scattering are frequently possible as a function of the absorber atomic number. So you can see that we have mentioned that the photoelectric effect increases with atomic number that we have already mentioned. The line at the right represents the energy at which Compton scattering and pair production are equally possible. Three areas are thus defined on the plot within which photoelectric absorption, Compton scattering and pair production each dominate. Now, we are not mentioning more about the photonuclear absorption that we have just mentioned the name, this one. The photonuclear disintegration, and this is already we have mentioned in your nuclear physics topics. That means when a photon is incidenting on a nucleus, it disintegrates by absorbing that gamma, and this is not at all important for us. And next is gamma ray attenuation. We will be defining some attenuation terms for gamma ray. As you know, attenuation means it is a decrease in its intensity or amplitude. When mono-energetic gamma rays are collimated into a narrow beam and allowed to strike a detector after passing through an absorber of variable thickness, the result should be simple exponential attenuation of gamma rays as shown in figure below. This is similar to our electronic absorption, and this type of experimental range we have already discussed. This T you can vary. So when the thickness increases, I by I0 is coming like this. This I0 is the incident intensity and I is the transmitted intensity. and each of the interaction process removes the gamma ray photon from the beam either by absorption or by scattering away from the detector direction, and can be characterized by a fixed probability of occurrence per unit path length in the absorber. The sum of these probabilities is simply the probability per unit path length that the gamma ray photon is removed from the beam. So, a probability for removing a gamma ray. So, and that probability for removing is due to these three, and you are now writing the linear attenuation coefficient mu as it is a sum of the probability of photoelectric, Compton and pair production. Tau for photoelectric probability, sigma for Compton scattering, and kappa for pair production. The number of transmitted photons I through an absorber of thickness T in terms of the number transmitted without an absorber I0 is given by I equal to I0 e raised to minus mu T. The gamma ray photons can also be characterized by their mean free path lambda. Mean free path means actually in collision you are normally taking that in solid state physics. So, it is defined as the average distance traveled in the absorber before an interaction takes place. So, it is the interaction distance gamma ray can travel before an interaction. And you can see that it is actually inversely proportional if the probability of absorption is high. That means if you are directly absorbing a gamma ray very easily, that gamma ray cannot travel large distance. That means when absorption probability is high, the mean free path will be less. And if the absorption is less, you can see that that gamma ray can travel more distance without any absorption. That means its scattering length will be, or its mean path lambda will be large. That is why you are saying that this mean free path, it is the reciprocal of the linear attenuation coefficient. Lambda equal to 1 by mu, and you are now considering this mu as the probability, which is the sum of these three. And typical values of lambda range from a few millimeter to tens of centimeter in solids for common gamma ray energies. Use of the linear attenuation coefficient is limited by the fact that it varies with the density of the absorber, even though the absorber material is the same. Therefore, the mass attenuation coefficient is used. It is defined as, we will explain this concept as mu by rho as mass attenuation coefficient, where mu represents the density of the medium. In last we have mentioned a term as tau by rho. I think you are remembering that. And for a given gamma ray, the mass attenuation coefficient does not change with the physical state of the given absorber. We have mentioned that with the change in density, this mu is changing. But if you are considering mu by rho, it is not at all changing. For example, it is the same for water, whether present in liquid or vapor. The mass attenuation coefficient for a compound or mixture of elements can be calculated by the relation. This is a statistical equation. Your mu by rho for a compound you can write as sigma over I, Wi mu by rho of I, where this mu by rho of I for a particular ith component in the compound, and Wi factors represents the weight fraction of the element I in the compound or mixture. Next is absorber mass thickness. In terms of the mass attenuation coefficient, the attenuation law for gamma rays now takes the form I by I0 equal to e raised to minus mu by rho into T. you are writing it as mu by rho into rho t. Actually, the initial expression was minus mu t. We have divided by rho and multiplied with rho. That means it is minus mu by rho into rho t. And this mu by rho we have already defined. And the product rho into T is known as the mass thickness of the absorber. T is the thickness. When you are multiplying it with the density or mass density, actually that rho is mass by volume, that you are calling the mass density or simply the density. So that is why this is called as the mass thickness, product with the mass term. The significant parameter that determines its degree of attenuation. This is the significant factor. Units of mass thickness have historically been. This is the unit that we have been using for so many years. So that is why you are considering it as milligram per square centimeter. The thickness of absorbers used in radiation measurements is therefore measured in mass thickness rather than physical thickness because it is a more fundamental physical quantity now. So you will be saying that it is in mass thickness you will be saying and not directly the thickness. The mass thickness is also a useful concept when discussing the energy loss of charged particles and fast neutrons. For absorber materials with similar neutron or proton ratios, a particle or neutron by proton ratios, a particle will encounter about the same number of electrons passing through the absorbers of equal mass thickness. Therefore, the stopping power and range when expressed in units of rho t are roughly the same for materials that do not differ greatly in set. So if Z is almost same, this term rho t will be nearly same. T may be different, but your rho is also changing. So, but that product rho, that means when rho increases, T decreases. So that product rho T remains same. And another term built up. The gamma ray built up means actually you are increasing or adding. That is the meaning of that term. The gamma ray attenuation experiment in which the gamma rays are collimated to a, this is not tau, it is to a narrow beam before striking the absorber, is sometimes characterized as a narrow beam or good geometry measurement. The essential characteristic is that only gamma ray from the source that escape interaction in the absorber can be counted by the detector. That means here you can see from a source, this is the direct rays you are getting, and actually these are not coming to this side or for that absorber, but it is scattered from somewhere and it is also coming to the detector. So actually now detector is measuring the direct as well as scattered. So your detector has the technique to count the direct as well as the scattered one. Scattered one means it is the escape interaction, that you can call that term. Real measurements are often carried out under different circumstances in which the severe collimation of the gamma ray is absent. Now, the detector can respond either to gamma rays directly from the source, to the gamma rays that reach the detector after having scattered in the absorber, or to other types of secondary photon radiation. So, this gamma ray can produce some other mechanisms, and from there, gamma rays can be again produced. Many types of detectors will be unable to distinguish between these possibilities. That means you can't detect it as from source, scattered, a newly generated gamma, that you can't distinguish. So that the measured detector signal will be larger than recorded under equivalent good geometry conditions. If In good geometry condition, you will be getting only this. And in bad geometry condition, you are getting this. That means this number will be larger than the normally that we are expecting. And the conditions that lead to the simple exponential attenuation are therefore violated in this broad beam or bad geometry measurement because of the additional contribution of the secondary gamma rays. So, this situation is usually handled by replacing the expression for intensity as, actually we have written as I is equal to I0 e raised to minus mu t. You are using a constant or term, a factor known as B of T and E gamma. T is the thickness and E gamma is the energy, where the factor B of T E gamma is called the built-up factor. The exponential term is retained to describe the major variation of the gamma ray counting ray with the absorber thickness. This must be there. And the built-up factor is introduced as a simple multiplicative correction. The magnitude of the built-up factor depends on the type of gamma ray detector used because this will affect the relative weight given to the direct and secondary gamma rays. The build-up also depends on the specific geometry of the experiment. As a rough rule of thumb, the built-up factor for thick slab absorbers tend to be about equal to the thickness of the absorber measured in units of mean free path of the incident gamma rays, provided the detector responds to a broad range of gamma ray energies. That means you are using a wide range of gamma ray. So, you can see that build-up factor is almost equal to the thickness of the absorber. So, that is a way of finding that factor. And that's all in this gamma ray interaction as well as some terms regarding its attenuation. Thank you.